All right, guys, let's go ahead and get into it. Okay. So, on Friday of last week, we discussed the probability, like just some basic probability stuff. We did that simulation with the dice. All right. Now, a couple of things before we get started. So, as you know, Canvas is still down. Okay. It looks like for the foreseeable future, it will be. So, last Friday, I emailed everyone the OneNote link. All right. So, if you got an email from me, it has the OneNote link on it. My recommendation at some point, either book, yes, it shouldn't be. I'll double check, but it shouldn't be. Um, but that's where I'll be posting things from now on. So, for example, the assignments, if you look at the very top of the Unit 7 stuff, there's the one from last week. All right. So, and I even figured out if you click this, it'll go right to the part where you have to do. All right. So, again, if there's issues with the link, just let me know. Because I know, like, I think I had one kid in my other class period that like it looked like it was blocked by admin, but the rest of everyone else could get in, so it was weird. I don't know. It's weird. Anyway, just let me know if you can't get into it. But for this foreseeable future, that's where I'm going to be posting pretty much everything. Okay. So I emailed that to everyone last Friday. So my recommendation, bookmark that link or something so you have access to it. All right. So we did the probability simulations last week. Now we're going to actually go into some of the basic probability rules and stuff. Okay. So one of the biggest things with mathematics is trying to figure out how to quantify chance. And that's exactly what probability does. So with probability, we assign a number to how likely an event is to occur. And the biggest thing with probability is that's very vocab heavy. All right, so you got to know what these vocabulary words mean. So here's some of the basic terminology for probability. So we have experiment, which is some process that occurs with well-defined outcomes. So for example, when we did that dice simulation last week, that was technically an experiment. Our outcome is the result from a single trial of an experiment. Equal likely outcomes is when outcomes of an experiment all have the same chance of occurring. So can anyone think of something that the outcomes will all have an equal chance of happening? So like all right, so I want you guys to think about things that you've done to test probability before. What kind of material or manipulative could you use that the outcomes will be, you have the exact same chance of getting that different outcomes? Flipping a coin. Good. So that's a 50-50 shot getting heads or tails. Can anyone think of something else? Rolling a dice. All right, a singular dice, not two. All right, if you roll a dice, you have a 1/6 chance of landing on any of the numbers. Can anyone think of another? Those two are probably the most common. Another one would be, say, a spinner, as long as the sections of the spinner are the same size. All right. Then we have an event, which is a collection or set of one or more outcomes. And finally, we have the sample space, which is a collection or the set of all outcomes of an experiment. So let's actually put those into practice. So an experiment is run where a spinner is spun once around a circle with 5 equal sectors that have been marked off as shown. So that means every piece of the spinner is exactly the same size. So what is the experiment here? So what's happening? What are we testing? It's pretty obvious, guys. So what are we looking at? What are we actually doing? So we have a spinner and we're spinning it. So what's the experiment? What are we looking to see? Where what? See where the spinner lands. That's exactly what the experiment is. We're trying to see where the spinner lands. All right. Someone name me one outcome of this experiment. So what is one outcome of this experiment? 3 is. All right. What's another? 1. What's another? 4. What else? 5 and 2. So all of these are outcomes. Now, if we put it into these little brackets, these are not only the outcomes, this is the sample space. These are all the outcomes that can happen. Now, it then asks, what is the probability of spinning the spinner and landing on an odd number? So, how many odd numbers are there on the spinner? 3. 1, 2, 3. Of how many total? 5. So the probability is 3/5. So the probability of landing on an odd is equal to 3/5. Now, it then asks, what is the event here and what outcomes fall into the event? So, what's the event? What are they looking for? So, what are we looking for? What do we want to happen? We want to land on an odd number. So, the event is we want to land on an odd number. All right. What would the sample space be? Or what would not the sample space, what would the set be for that event happening? So what numbers fall into that event? 1, 3, and 5. So 1, 3, and 5. All right. Now, so there's a very basic formula with probability. This is kind of like the bread and butter with probability. And it basically says the probability of event E happening is this ratio. Now we write it as the probability of some event E. So like, for example, this is like what I wrote here, the probability of an odd number happening, where you have N of E over N of S, where N of E is the equally likely outcomes that fall into event E, and N of S is the number of equally likely outcomes that fall into the sample space. So if you look here, This is the number of outcomes that happen in the event. This is the number of outcomes that happen in the sample space. Now, given this definition, between what two numbers must all probabilities lie? So if we keep it as a fraction, most probabilities are written as fractions. All right. What two numbers, and we talked about this last week, what two numbers must the probability lie between? Think about it percentage-wise. So if we're talking percent, what percent can we not go over? 100. What's that in terms of a fraction? 1. So 1 is the number that we can't go past, but what's the lowest number we can have for probability? 0. All right, so the numbers that we cannot go between are 0 and 1. Why do you think that is? Why do you think I can't go below 0 or greater than 1? Because what? Say it one more time. So we can't have. Say it one more time. Right, below 0 can't happen because negative numbers, right? Why can't it go past 1? Right, there's more outcomes than possibilities. It doesn't make sense. Okay, so 0 can't go under 0 because negative numbers. We can't have negative probability. 1, oh my gosh. And we can't go past 1 because then we would have more outcomes than possibilities. Yeah. Now, we talked about this last week, but we then have something called theoretical probability. So in this class, that's typically what we work with unless we're running an experiment. So we don't have to always run an experiment to determine the probability of an event happening. We just simply have to know the number of equally likely outcomes in the sample space and the number of those outcomes that fall into an event. All right? So why is this being stupid? So let's look at exercise 3. A fair coin is flipped 3 times. What does it mean by a fair coin? Say what? It's an equal probability, all right? Meaning it's not weighted so that it will always land on one side. It's not manipulated anyway. Now, the sample space consists of the ordered triples such as heads, heads, tails. So in other words, if you flip the 3 coins, one of them land on heads, one of them land on heads, the other one land on tails. So it represents a head on the first toss, head on the second toss, and a tail on the third toss. So we're going to draw a tree diagram to show the different equally likely outcomes in the sample space. So how tree diagrams work, you start with your first flip. So on my first flip, what are the two outcomes that can happen? Heads and tails. So this is my first flip. Now, my second flip, what can happen? So what can happen on second flip? Heads or tails, but we also got to take into account the first flip. So let's say the first flip was heads. The second flip can be heads or tails. Let's say the first flip was tails. The second flip can be heads or tails. So this right here is the second flip. And then finally the third flip. So with the third flip, we can also get what for all of these? Heads or tails. So this can all represent the third flip. So the way a tree diagram works, and you guys have probably seen one before, but if you just follow a path or one of the branches, that is one possible outcome. Okay, so when it says to list all of the ordered outcomes, that means we're listing the sample space. The first one that I highlighted was heads, heads, heads. So all three were heads. Someone name me another outcome. Tails, tails, tails. Okay, so we just took care of this one. What's another one? Heads, tails, tails. Okay, so we did this one. What's another one? Tails, heads, heads. Okay, so we did this one. What's another one? Tails, heads, tails. So we did this one right here. What's another one? Heads, tails, heads. So we did this one right here. What's another one? Heads, heads, tails. So we did this one right here. There's one more. Tails, tails, heads. So that was this one right here. So that's how you pull all the different outcomes out of a tree diagram. You literally just kind of go for all the branches. All right. So this would be my what? What's this called? Your list of all outcomes is called the what? Sample space. So this is my sample space. So let's get some probabilities here. So looking at my sample space, what is the probability that I will get all heads? So first off, how many total outcomes do I have?
There are 6.
There,
Or there are.
there's 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So everything that we're going to have is going to be over 8. How many have all heads? 1. Only one outcome has all heads. So the probability of getting all heads is 1 over 8. The next one, probability of getting exactly 2 heads. So not, you don't want more than 2 heads. You don't want less than 2 heads. You want exactly 2 heads. So once again, there's 8 outcomes. So whatever we get is going to be over 8. How many outcomes in that sample space have exactly 2 heads? There's 3. 1, 2, 3. So they don't really care the order of heads. They just want to know which one had exactly 2 heads in them. And then the last one, all heads or all tails. Remember, or in probability means at least 1, meaning we want to know where we have all heads and where we have all tails. So for all heads, what's the probability of getting all heads? We already found it. 1 over 8. What's the probability of getting all tails? 1 over 8. So what's the probability of getting either one of those? 2 over 8. You would add those together. And 2 over 8 simplifies down to what? 1/4. Divide both the top and the bottom by 2. All right. Last thing, sometimes we must quantify chance by using observations that have been made in the real world. In this case, we're talking about empirical probability. So in other words, we take what we got from an experiment and we start looking at the probabilities. So a survey was done by a marketing company to determine which of 3 sodas was preferred by people in a blind taste test. Have you guys ever seen like those Coke or Pepsi commercials where like 90% of people chose Coke over Pepsi in a blind taste test? That's what they did. Okay. They gave them like, a cup, and they had like 3 different brands that all pretty much looked the same, and they made them taste them and then pick out which one was their favorites. They had no clue which was what. So the results are shown here. This is what we call a frequency table. All right, so this right here is what we call a frequency table, just so you know. How many times something happens. So it says to find the empirical probability that a person selected at random from this group prefer soda B. Okay, so we want to find the probability that the person chose soda B. First off, let's figure out how many people total, or how many total outcomes there were. How many total outcomes were there, or how many people were tested? 53. So this was the total number of people that were surveyed. So that's going to be the bottom. Now, how many people like soda B? 24. So that's what's going to go on top. Now, put down your calculator and tell me that as a decimal to 2 decimal places. So round to 2 decimal places. So what was it? If you do 24 divided by 53, what'd you get? I saw you put in your calculator, guys. Someone tell me.
0.445.
0.45. Now, what would that mean? How many people preferred soda B if you were thinking percentage? 45%. So we can also say that it was approximately 45% of people like soda B. So these are the three different ways you can write probabilities. The ones that you'll probably be asked to the most are these two. Occasionally they'll ask for it as a percentage. All right, but more often than not, you start with it as a fraction and they may ask you to convert it to a decimal. All right, find the empirical probability that a person selected at random of the group would not prefer soda A. So we want the probability of not soda A. Okay, so how do I figure this out? First off, how many people were total? How many outcomes do I have? 53. That's still the denominator. Now, we don't want soda A. Yes, sir. Right, we're going to add B and C. So we're going to add 24, which is B, plus 11, which is C. Right, so this is the probability of B plus the probability of C. That would equal 35 over 53. So what's that as a decimal? To two decimal places. 0.66. So as a percentage, that would be about what? 66%. So about 60%, 66% of the population did not like soda A. Or they did not prefer soda A. All right, now, that's it for lesson 7.1, but I also want to do one last thing. So go to page 5. Now, I know this says honors, but honestly, like Venn diagrams, I feel like everyone should know how to do. So when it comes to Venn diagrams, all right, what do Venn diagrams typically show? So you guys have been doing these like forever. What do Venn diagrams typically show? Well, show statistics. It's more of a way to organize information. But a lot of times, what will Venn diagrams, what's really helpful about Venn diagrams? They can show you the what's. The groupings and the overlaps, right? Can't you see like where all the overlaps are? Yeah, that's what's good about Venn diagrams. So, a survey of faculty and graduates at the University of Florida's Film School revealed the following information. 51 admire Mo, 59 admire Larry, 60 admire Curly, 34 admire Mo and Larry, 32 admire Larry and Curly, 36 admire Mo and Curly, 24 admire all three of the Stooges, and 1 admires none of the 3 Stooges. So, before we can even answer these questions, we got to start putting stuff in the Venn diagram. Now, let's think logically about this. With these first 3, they didn't say that they just admire them. All right? Admired like a singular one. They just say that they admire them. That means that they can be included in the both. Okay? So we're not going to put 51 here for Mo. What it's saying is that if we add up everything in this entire circle, it'll be 51. So here's my question. Which of these statements would make the most sense to start with your Venn diagram? Say it again. Well, we don't know that yet. We can get that from the Venn diagram. What I'm saying is that when we're making our Venn diagram, which of these statements would make the most sense to start with if we want to figure out where all the overlaps are. What's the biggest overlap in a Venn diagram? Say it again. The what? Well, yeah, it's a number, but what's the biggest overlap? So in other words, is the overlap going to be just with two of them? Or is it going to be all of them? Or is it going to be all of them? Whenever you do a Venn diagram and you have to fill it in on your own, you always start with the overlap. So you start with the all or the middle. So you start with the middle. Because that means that 24 and my are all three of them, that goes dead in the middle. So what happens is that for all the other overlaps, we're going to have to take into account that we already have 24 of them, then my are all three. Okay, so whenever you do a Venn diagram, you start in the middle and you work your way out. So let's just keep going. 36 admire Mo and Curly. Okay, so we're going to look at the Mo and Curly. They're saying that 36 admire Mo and Curly, but that includes the overlap of that 24. So how many just admire Mo and Curly? They don't like Larry. What was it? Not 16, 12. You're going to take 36 and subtract 12 to it. That's how many just like Mo and Curly. Or 24. So just Mo and Curly, you're going to take 36 and subtract 24. That gives you 12. All right. 32 admire Larry and Curly. So they can still like Mo, but 32 total like Larry and Curly. So how many just like Larry and Curly? How you know? Right, you do 32 minus 24. So you take how many admire them total, subtracted from the ones like all three, and that'll give you the just, which is 8. You guys kind of picking up what I'm putting down here, how this works? All right, that's why the wording is very important, because they didn't put the word just there, or only. Only is another word, okay? All right, so 34 admire Mo and Larry. So Mo and Larry, 34 admire them. But how many just admire Mo and Larry? So they don't like Curly. How many of them just like Mo and Larry and not Curly? 10. You do 30. You do 34 minus 24. That'll give you 10. So we got all of the overlaps filled in. Now we need to figure out the ones that only like one of them. And that's where the overalls come from. So it then says that 60 admire Curly. So 60 total people admire Curly, and that includes the overlap. So we're looking at this entire circle right here. So here's the question. How many only like Curly? So 60 admire him total. How many only like Curly? How do you figure that out?
60 minus 24.
More than that. Minus 12 minus 8. So you got to subtract all three of these pieces that are in the yellow circle. So how many only like curly? 16. All right. See if you can figure out how many only like Larry. Take a minute, figure out how many only like Larry. Thumbs up if you're ready. Okay, I'll give you guys one more minute. So if we're talking Larry, we're talking this circle right here. Just take that into account. If you think you got Larry, try Mo. I knew I forgot to include someone in the email. Yeah, I'll send you one. So I sent all the. All right, so we only want Larry. All right, now 49 admire Larry total. So let's go with Arieli. How'd you figure out how many only like Larry? Say it again. Mm-hmm. And which numbers are those? So you do 24, 10, and 8, and then you're going to do what to them? Subtract them by 40 from 49. Yeah, subtract from 49. So we're going to do 49 minus 10 minus 24 minus 8. So what'd you get? All right, 7. Is that what y'all got? All right, so 7 like Larry. All right. Then finally, 51 admire Mo. So let's go with Caden with a K. How'd you figure out how many liked Mo? Okay. Let's go with Cohen. How'd you figure out who liked Mo? All right. Let's go Riley E. How'd you figure that out? Good. So you look at the entire circle, which is right here, and subtract out the overlaps. And what'd you get? 5. Good. Now, there's one last piece of this Venn diagram that we're missing. What's the only statement that we haven't done yet? Say it one more time. No, there's one statement on that list that I've been highlighting that we haven't done yet. What's the only statement we haven't done? One admires none. Now, that we still need to include that. Where do you think I would put it? Right. So you need to put the one on the outside of the circles. So the rectangle represents the sample space. So this rectangle represents the sample space. So anything that does not fall under within the circles, you put outside the circle. So they don't like any of them, they go outside the circle. Now we can answer the question. So how many people were surveyed? How do you think I'm going to use this Venn diagram to figure out how many people were surveyed total? Add up all the numbers. So we can't add up the ones from the statements because there's too many overlaps. But if you look, we separated them all, and we took out all the overlaps essentially. So we're going to add up every last one of these numbers. So we're going to do 5 plus 10 plus 7 plus 12 plus 24 plus 8 plus 16 plus 1. Don't forget the one on the outside. So when you add up all of those numbers, what do you get? Say it one more time. 83 people. So there were 83 people total that were surveyed. Now, it wants to know how many people admire Larry or Curly. So think about this carefully. All they got to do is just admire Larry or Curly. They can admire both. They can admire them and Mo. All right? But Larry or Curly has to be in that statement. So how do you think I figure out how many that is? Subtract what? Not quite. So which color circles are Larry and Curly? Yellow and orange. Okay, so that means that every number in the yellow and orange circle we want in our calculation. So what's the only two numbers that are not in our calculation? 5 and 1. Okay, so in reality, we're looking at all of the numbers in these two circles. That's what we're going to add up. All right, so we're going to do 16 plus 12 plus 24 plus 8 plus 10 plus 7. And the reason we do that is because they just said Larry or Curly, which means at least one. And I know I skipped letter B. That's my bad. Come back to it. Meaning as long as they like one of them, it doesn't matter if they also like Mo. It doesn't matter if they like all three. It doesn't matter if they like both Larry and Curly. All right? So how many like Larry or Curly? So when you add them up, what do you get?
77.
77 people. Now let's go back to B because I skipped it. It says, how many people admire Curly but not Larry or Mo? So in other words, they only like Curly. How many people only liked Curly? 16. Number of people that only like Curly it's the only number in the Curly circle that does not fall in an overlap. So 16 people like Curly. Only. Now, the next question, how many admire exactly one of the Stooges? So how many people admire only one of the Stooges? So they only like Mo, or they only like Curly, or they only like Larry. How do I find that? Keep going. Say one more time. Add what up? Okay, so which number specifically? 5, 7, and 16. Good. You're going to add up all the numbers that are not in overlaps. So we're going to add up 5 plus 7 plus 16, which is what? 24. So 24 people only like one of the Stooges only.
Ms. Murphy. Is it 5 plus 7 plus 16?
28. It's 28, yeah. All right, last one. How many admire exactly 2 of the Stooges? So they don't like all 3, but they don't like just one either. They like exactly 2 of them. So they like Mo and Curly, or Mo and Larry, or Larry and Curly. How do I figure that out? So we know we're going to be adding up numbers, but which ones? Which numbers represent liking only 2 of the Stooges? Say it again. So the ones that are between the 2, so all the overlaps except for what number? 24. So we're adding up all of the overlap numbers except for 24. Why are we not adding 24? Because that represents liking all 3. We want the ones that want exactly 2. So we're going to do 10 plus 12 plus 8. And that'll give me what? 30 people. So does everyone understand how you use Venn diagrams to get information and how to set them up? Okay. So your homework for tonight is pages 3, 4, and 6. So you guys got a solid 40 minutes. You can probably knock it out now. So 3, 4, and 6 is your homework tonight. Now, as you're working on this, I'm going to come around and, yes, ma'am. Yeah. As you're working on this, I'm going to come around at some point before the end of class and check off that checked understanding on that blue sheet. All right, so make sure you have that out. I'll come around just a minute to check that off.